Welcome everyone. So today I am doing a lesson on functions. Functions is basically the basis of college algebra, so this will give you a good leader into that. So we're going to start with the concept of a relation. So a set of ordered pairs is called a relation. So everything that we looked at last week when we were graphing, those were relations. A relation is just showing a relationship between two things. So if there's some sort of relationship, we don't know what it is, but they're related in some way, it's a relation. The x values are called the domain and the y values are called the range. So I have an example here of a relation. It is a set of ordered pairs. So it has set notation, the curly braces, and then there's ordered pairs in there. So the x values are always the first value. So our domain is a set, and it's set of all of the x values. So we have an x value of 2, -4, -3, and 4. So I'm just listing off all of the x values. They don't have to be in order. And then the range is the y values. Now, if it's already listed, you don't have to list it twice. So the y values have 5, 17, and -5. The fourth point has 5 as a y value. Again, that's okay, because I already listed it. So as long as it's listed, I don't have to repeat it. So that's the domain and the range. The domain is considered the input value, and the range is the output. So if we look at functions, a relation is a function if for every element in the domain there is exactly one value of y in the range. So if you plug in numbers essentially and you get only one answer, that is a function. So there are tons of relationships in the world, but not everything is a function. So things that are functions, though, are very useful. So that's why you study them in college algebra. So a function has one output for every input. You could be plugging in multiple inputs, but you get one answer out. So this is the same example I had before. The question is this a function? So the way I look at it is I sort of map out the x and y, the domain and the range. So I'm going to list my x values. I should have made this box a little bigger. And then my y values, the range. Then I draw arrows. So I have an ordered pair 2, 5. So you plug in 2, you got 5 out. -4, 17. -3, -5. And 4, 5. So you plug in an x value, you get a y value out. Every input has only one arrow from it, which means there's only one output. So that makes this a function. Because every input only has an arrow going to one output. It's okay to have an output repeated as long as they're coming from different inputs. So this means this is a function. You can only have one output based off of what you're plugging in. If we look at these graphically, we can determine if an equation or graph is a function by what's called the vertical line test. So if you can draw a line anywhere on the graph, and if you hit the graph more than once, it's not a function, because that means there are two outputs, because the y is the output. So on the left here, if I just draw a line right here, I am hitting the graph twice when I draw that vertical line, which means for whatever that input is, that x value, there are two different y values. So this means it's not a function. It fails the vertical line test. Now the second graph here, it doesn't matter where I draw a line, I will only hit the graph in one spot. So because you only hit the graph in one spot, that means this is a function. So your goal is to determine if to use the vertical line test is to try to hit the graph more than once. So you want to try to prove that it's not a function by trying to draw specifically a line where it hits the graph more than once. And then that means it's not a function. If it's impossible, then it's a function. So when things are functions, we have special notation so that we know that it's a function. And instead of using y, we use this, f parenthesis x parenthesis. This is read out loud as f of x. So this is a special notation. It goes together. It's like a new symbol. It's a combination of symbols to create a new symbol. It does not mean f times x. That's not multiplication. This is specific notation. So f of x is telling us that we have a function, that's f, that's why they chose f for function, and x, where x is the input. So that notation tells you that your function is called f and you're plugging in for x. So it's telling you the input. Y is the same as f of x if you have a function. So anytime you see f of x, you can replace that with y. So you could write y equals 2x plus 5 instead of writing f of x equals 2x plus 5. However, if you have a y equals, you can't always write it as f of x because you don't know necessarily if it's a function unless you use the vertical line test. But if you're given f of x, you can always replace it with y. So they are essentially interchangeable if you have a function. So let's look at some examples of function notation. So we're going to start with evaluating a function. So this is very important. We have the word evaluate. We never solve for a function. We are never solving for f because f is not it's not f times x. So in this case it'd be g. We would not be solving for g. It's not g times x. It's a different notation. So you're never solving for a variable. You're only evaluating. And evaluating means performing the order operations to simplify. So we're doing the order of operations. And we always do it on the right side because we always write our function notation on the left. So you're only simplifying the right. Just write that out. Only simplify the right. So now let's see what this looks like. So we have a function g of x. This is just another name instead of f. We can call it g. If you wanted to, if it meant something, like you can use a word there, call it function of x, and actually write the whole word instead of a letter. That's completely fine. G of x equals x squared plus 1. Find the following. So g of -2. So you want to follow the pattern here. Our function notation has g of x. If we have g of -2, that means that x is equal to -2. So it's telling us x is -2. So we need to replace x with -2 on both sides. So you're also doing it on the right side of the equation. So I'm plugging in -2 everywhere I see x. And now we're evaluating, so we're only following the order of operations on the right side. The left side stays the same. So it's usually easier to not even touch the left and just keep writing down on the right. So order of operations say we have to do the exponent, -2 squared, that's +4. So I have 4 plus 1, and this equals 5. So we can write our answer as g of -2 equals 5. What is nice about function notation is instead of saying y equals 5 and then forgetting what you put in for x, you can see what your x value is and you can see what your y value is. So it gives you both pieces of information. We can also write as an ordered pair -2, 5. So both of those are acceptable ways to write your answer. Now notice I did not solve for g. I'm not dividing both sides by -2 to get g equals. That's not what we're doing. We have to leave the left side alone because we have function notation. So it's really important to recognize when you have function notation. It is written specifically where you have your variable with your x, your input, in parentheses. If it said gx and there were no parentheses, then you would be solving. But the parentheses tell us that this is a function. So it's really important to know the difference there. Now the second example here I have is g of 3. So that is telling us that x is equal to 3. So I have g of 3, and then I have to plug 3 in for x. So that's 3 squared plus 1. So now I'm only following the order of operations on the right. 3 squared is 9, so that's 9 plus 1, which is 10. So we get g of 3 equals 10 as our answer, or you can write this as 3 comma 10. So note the pattern when you're evaluating. You're doing the same thing, you're just doing it with a different number that you're plugging in. So definitely pay attention to the patterns. Now let's take a look at evaluated function in a real world situation so that you can see what does this mean, what does this tell us. So the number of people diagnosed with skin cancer we're calling n of x. So they chose n to represent number. So that's the nice thing about function notation is you can choose a letter that sort of makes sense. So the number of people diagnosed can be approximated by this equation. So this equation is going to tell us how many people are diagnosed with skin cancer. So we know that the output is the number of people. For this function, x represents the number of years since 2003. So that means your x that you're plugging in are years. Now you have to pay attention, it's years since 2003 because n of 5 would be 5 years since 2003. That would be 2008. So you do have to pay attention to what they're calling the variables. So here they're telling us evaluate n of 0. N of 0. And then interpret the meaning in the context of the problem. So whenever you have word problems, you should always put it in context of the problem. So let's start by finding n of 0. N of 0 means that x is equal to 0. So I need to plug in 0 for x on the right side as well as on the left. So I have 45,625 parentheses 1 plus 0.029 times 0, because x is 0. Just grab my calculator here. So if I just highlight everywhere we see x in the original problem, that's where we're seeing 0 in our evaluation. So order of operations says that I need to do what's inside the parentheses first. And that means inside the parentheses, I need to do the multiplication first. So 0.029. Now, normally this is pretty simple to do in your head, but I'm going to show the steps. 0.029 times 0 is 0. So that's just 1 plus 0. So still following the order of operations, 1 plus 0 is 1. So that's 45,625 times 1. And then you multiply, you get 45,625. So n of 0 equals 45,625. So we evaluated that. The next step is to interpret the meaning in context of the problem. So what does this tell us? If you went around and you just told somebody that, they wouldn't know what it means. So let's look at our input. We plugged in 0. X is the number of years since 2003. So this is x equals 0 is 0 years since 2003. So that is basically in 2003. So I'm going to say in 2003, comma. So that's what we plugged in. Now what's the result, the output? So n is the number of people diagnosed with skin cancer. So in 2003, the number of people diagnosed with skin cancer, it'd help if I spell that right, cancer. So I'm just taking the context from the problem. The problem is telling us all of this. And then, okay, what is the result? What is the output? So in 2003, that our number came out to be 45,625. That means the number of people diagnosed with skin cancer is 45,625. So that is what this means in context. You have to give it context so that your numbers mean something. We're saying, okay, in this year, this is how many people were diagnosed with skin cancer. Now let's take a look at domain and range of functions when they're graphs. So when I talked a little bit about domain and range of a relation, you can also find domain and range of functions. We did it by ordered pairs. What happens if you have graphs? You still have to read the x and the y values. So the domain are all the inputs or the x values. So on the left here, I'm going to read the ordered pairs, and I'm going to go from left to right. So I have a blue dot. My first blue dot, the x value is at -5. Now my next blue dot, the x value is at -1. Then moving over, my next one is at 2, and then at 3. So I'm just reading the x values for each of these. So if I draw a line to where they are on the x, that's -5, -1, 2, and 3. So then the range is the output, the y values. So I can do something similar, and we always start with smallest. So the smallest number, if I go and kind of hit it to the y, is at -3. Then I have -1. The next one is at 4, and then 5. So I'm just taking the ordered pair, and then I'm just kind of mapping it to the x-axis to figure out what the range is. So you're just kind of flattening it out so you can figure out, okay, what are those output values? So now let's look at the one on the right. So this is a little more difficult because we don't have points anymore. We have a continuous graph. So if I tried to map this, I'd have like an infinite number of points is kind of get hit everywhere. And so you can see that basically, I'm starting with my domain, like I can just map everywhere on the x-axis if I try to combine that. So I'm going to just grab a highlighter here. And that whole thing here is connected there. So basically every x value would be hit if I kind of flatten this out and try to smush it down. Like pretend you're trying to take your graph and you're smushing it. It's going to hit everything on the x. So the domain is the x values, and if it hits everything, that means it's all real numbers. Because every number works. Now there is special notation called interval notation where we write -infinity to infinity. We haven't covered this in the reading, but I do have a link in the weekly content, or it might be in the supplemental materials. I don't remember where I put it, but there is a link on interval notation so you can see how you write that. So that is the domain. So now let me erase this so we can take a look at the range. So the range is the y value. So you're flattening it, but you're flattening it vertically instead of horizontally. So this would flatten, all of these would flatten, you know, all of these onto here, and then these would flatten the other direction. And then this arrow means that it goes on forever, so we can flatten those as well. So what happens when I draw the highlighter this time is that we're not doing everything. We're doing 3. 3 is the highest value there. We don't have anything graphed higher than 3. So here our range is restricted, but we have any number below 3. So you can write this as x is less than or equal to, not x, our range is y. Y is less than or equal to 3. Just all the y values that you're allowed to have for the range, they are less than or equal to 3. We talked about inequalities and the less than equal sign. That was all in week 1. We haven't really covered it since then, but we're just saying that the y values are less than or equal to 3. We're including 3 because that's our highest point. Now, an alternate way to write this would be in interval notation. Again, I have a document that shows how to do this, but the way it would be written is you have a negative infinity, and then because you're going down forever, and down forever is negative infinity, and then we stop at 3, and then there's a bracket. The bracket means that we're including 3. It's a hard ending point. Once you hit 3, you're done. You don't have anything beyond that. So it's like a wall. So that's how you would write it if you were doing this in interval notation. I'm going to actually pull up our classroom so I can see where I put this so I can direct you guys to the correct spot. I can't remember if it's in weekly content. Okay, it is in weekly content, so I'm going to pull the graph up here. So weekly content, when you go to the required readings, you're reading 9.6, function notation evaluation, then interval notation. So there are 2 links here, so I'm going to click on the first one. And this is talking about how you write your answers. So it's going through the basics with X. If you had inequalities, what does it mean on the number line, and then how you write it in interval notation. So it's just demonstrating what this looks. And you can think of our X and Y axes as number lines, essentially. Because what I did is I flattened things out so that it's on a number line. Instead of looking at it in 2D, I basically forced it to be 1D. So that is one source. Pulling that back up. The second one says interval notation and inequalities. I believe this is the one I created. Yes, so this is the one that I created. So I put the symbol, whether something is less than or greater than. I used X, but if it's the same if you're doing range, it's Y. Just make sure you have your number line from smallest to largest. What it looks like in something called set builder notation, and then what it looks like in interval notation. And then I described the different symbols, all real numbers, that there's no solution, and then I provided some examples of graphing. The textbook also has some of this. So if I go to the textbook and go to section 9.6, okay, so this is chapter 9. I'm gonna wait for everything to load. So we only need 9.6. So I'm clicking on 9.6. And so we're talking about domain and range of a function. So I have to scroll down to 5. So scrolling, looks like it's still loading some stuff. Okay, so here's some examples. Domain and range of a function where they have actual graphs. And so it has some examples. You can see in blue that they flattened it like I did. And then they're looking at, okay, where are you between? Here you flatten it, it's the whole number line. So that's one where it's all real numbers. And then there are some examples here, and the examples are, the answers are shown. So there are some examples in the textbook. If you do want a little bit more practice with that, go back to chapter 2 and it says linear equations and inequality. So we didn't cover 2.8, but that's 2.8. Let me click on that, go to linear inequalities. It talks a little bit more about it. It's solving it. We don't need to solve. We are just writing what it means if something is less than or greater than. And so it talks about the graphing, what it looks like, and then it talks about the set builder notation and interval notation and kind of gives you some graphical stuff. But this is all in 1D. When we look at functions, we look at 2D. So that's why you have to flatten it to a number line, and then you look at what you have. So there are some examples here. And you can look at, you can say, okay, what does my graph look like if I flatten it? And then you can look at the notation so that you can see what the proper notation is. And then, yeah, it loves to jump up. I don't know why it does that. So that's what you need to know for this week. You'll learn more about domain and range in more detail if you go to college algebra. The most important thing I think this week is just understanding the function notation. So if you have any questions, you can email me, or you can send me a chat message, or you can give me a call. And hopefully you have found this helpful. Hopefully you have found all of these live sessions helpful, or the recordings if you watch the recordings. And let me know if you have questions.